Every mobile robot faces the same question. Where am I, and what does the world around me look like? Without a reliable answer, a warehouse bot crashes into racks, a drone drifts into walls, and an autonomous car cannot plan a safe lane change. Simultaneous Localization and Mapping, SLAM, is the foundational capability that lets machines navigate unknown spaces, update their beliefs as they move, and recover when the world surprises them. Without SLAM, even perfect manipulation fails because the arm reaches the wrong shelf. SLAM solves a circular problem. To know where you are, you need a map of landmarks and free space. To build that map, you need to know where the robot was when each measurement arrived. Move without a map and drift accumulates. Map without a good pose and walls bend, shelves duplicate, and corridors smear into nonsense. SLAM breaks the loop by tracking pose uncertainty and map uncertainty together, updating both as new evidence arrives. Probabilistic frameworks treat both pose and landmarks as uncertain until measurements reinforce them. Localization estimates the robot pose, position, and orientation in a coordinate frame, often extended to velocity and angular rate. Odometry from wheel encoders or inertial sensors gives short-term motion but drifts. Global localization matches sensor observations against a known map. Kidnapped robot recovery handles sudden relocalization after a human picks the machine up. A good localization layer publishes pose with covariance so planners know when the estimate is tight or dangerously uncertain. Monte Carlo localization maintains thousands of pose hypotheses when ambiguity is high. Maps come in several flavors. Occupancy grids mark cells free, occupied, or unknown, ideal for floor-level navigation. Point clouds capture dense three-dimensional geometry from LiDAR or depth cameras. Semantic maps label walls, doors, pallets, and people so behavior can change by category. Topological maps connect places as a graph for high-level routing. Metric maps preserve distances. Topological maps preserve connectivity. Production systems often maintain several representations at once. Drift is inevitable on long trajectories. Loop closure detects when the robot returns to a previously visited region and aligns the new observations with the old map. That global constraint collapses accumulated error like pulling a wrinkled sheet flat. Visual place recognition, LiDAR scan matching, and learned descriptors all contribute. Without loop closure, a robot that circles a building may think it ended somewhere entirely different. With it, the map snaps back into global consistency. Pose graph optimization distributes correction across the entire trajectory instead of patching one jump. Metric maps preserve real-world scale so a planner can reason about centimeters and meters. Topological maps abstract space into nodes and edges. Kitchen, hallway, loading dock. Metric maps excel at precise motion. Topological maps excel at long-horizon routing and human-readable instructions. Many deployments fuse both: a topological graph for mission planning and a metric layer for local obstacle avoidance. Choosing the wrong representation wastes compute or loses critical detail. Human operators often think topologically even when the planner uses metric grids underneath. Visual SLAM extracts stable image features or tracks photometric intensity directly. ORB SLAM popularized feature-based mapping with robust loop closure. DSO and related direct methods optimize on pixel intensities for fine detail. VINS mono and visual inertial systems fuse camera frames with IMU data for fast motion and short gaps when texture is weak. Cameras are cheap and information-rich, but they struggle in darkness, motion blur, and featureless walls. Rolling shutter and motion blur remain classic failure modes for fast mobile platforms. LiDAR SLAM builds maps from precise range returns. LOAM separates odometry and mapping for fast-spinning LiDARs on ground vehicles. Google Cartographer combines submaps, scan matching, and loop closure for indoor and outdoor fleets. FastLIO pushes high-rate inertial LiDAR fusion for agile drones and legged robots. LiDAR handles lighting variation well, but can fail on glass, long tunnels, and heavy rain without complementary sensors. Spinning LiDARs on drones demand motion distortion compensation during aggressive maneuvers. No single sensor owns every environment. Multi-sensor SLAM fuses cameras for semantics, LiDAR for geometry, IMU for high-rate motion, wheel odometry for smooth floors, and GPS when outdoors. Time synchronization and extrinsic calibration tie the streams into one state estimate. When one modality degrades, others carry the solution forward. This is why production autonomous stacks rarely ship camera-only or LiDAR-only localization for safety-critical navigation. Tight time synchronization is as important as algorithm choice for fused SLAM pipelines. In warehouses, AMRs share shelf maps, track dynamic pallets, and reroute around humans. Autonomous cars maintain lane-level maps and localize against curbs, signs, and prior LiDAR surveys. Delivery robots navigate sidewalks with semantic cues for crosswalks and ramps. Each domain stresses SLAM differently. Tight aisles demand centimeter accuracy, while urban driving demands robust relocalization across weather and construction changes. Construction changes and moved inventory mean maps need lifecycle management, not one-time builds. Drones map construction sites and inspect bridges with aerial SLAM when GPS is multipath prone. Mars rovers pioneered long-range visual odometry, where no prior map exists and communication delays forbid cloud assistance. Humanoids must localize while balancing, shifting viewpoint constantly as they walk. These scenarios push SLAM toward robust feature selection, aggressive outlier rejection, and maps that update when the world is not static. Planetary SLAM-inspired robust odometry techniques now reused in harsh terrestrial mines. Most SLAM systems split into a front end and back end. The front end tracks frame-to-frame motion, associates features or scan matches, and proposes new landmarks. The back end runs pose graph or bundle adjustment when loop closures arrive, distributing error across the trajectory. Outlier rejection removes bad matches from reflective glass or repetitive texture. Keyframe selection prevents the back end from choking on redundant similar views. The output is a consistent trajectory plus a map other modules can query for planning. SLAM fails in predictable ways. Dynamic objects like forklifts and pedestrians corrupt static maps. Perceptual aliasing makes identical corridors look the same, causing wrong loop closures. Sensor dropout, motion blur, and miscalibration inject silent error. Long-term mapping must handle seasonal change. Moved furniture, new construction, snow piles. Robust systems detect map inconsistency, mark region stale, and schedule remapping instead of trusting an outdated world model. Kidnapped robot recovery and relocalization after long drift remain active research fronts. Downstream modules expect more than a pretty point cloud. They need pose with uncertainty, occupancy, or cost maps for collision checking, semantic layers for rules like stay off grass, and quality flags when tracking is weak. SLAM succeeds when planners trust its outputs enough to move fast yet slow down when belief widens. Cost maps derived from occupancy let planners trade shortest path against clearance margins. SLAM is not glamorous, but it is load-bearing. Manipulation, inspection, and collaboration all assume the robot knows where it stands. As fleets scale, shared maps become infrastructure, updated centrally, versioned carefully, and validated before missions run. Investment in localization pays off every time a machine reaches the right dock or shelf without human rescue. SLAM answers the two questions every mobile robot must solve: where am I, and what does the space look like? Localization tracks pose and uncertainty. Mapping captures occupancy, geometry, semantics, and topology. Loop closure and multi-sensor fusion fight drift. Visual and LiDAR pipelines each shine in different conditions. From warehouses and cars to drones, Mars rovers, and humanoids, reliable SLAM is the bedrock that turns sensor streams into confident motion through the real world. Treat SLAM as a living service. Monitor drift, schedule remaps, and version maps like software releases.